Some of this look familiar, I hope, from Friday. Friday was somewhat chaotic. I know a bunch of you had to leave. So let's make sure we have all the pieces in place that we talked about on Friday before I talk about the stuff that's new. First, impulse has a cause and an effect. The effect is observable. The cause isn't always observable. Sometimes the cause happens way too fast. For example, most of the time you can't see the golf club hitting the ball. That moment in contact happens way too fast to be seen. But you can see the result. The golf ball was sitting there on the tee, and a few moments later, the golf ball is in the air. The effect of an impulse is easy to see, but often the cause is not. I want to remind you that the direction of an impulse, though, is in the direction of the force, not necessarily the direction of the momentum. I think I used the example, if you have a puck going this way, and then after an impulse, the puck is going this way, well, the impulse acting on that system had to act that way, right? Do you see why that has to be true? The impulse has to be in the direction of the force. So part of that force had to stop the motion of the puck when it was going this way and start its motion this way. So although neither momentum is in the direction of the impulse, the direction of the impulse is in the direction of the change. And that's the direction of the force. Force is change in velocity, right? Force is acceleration. So I do want to point out the fact that the actual technical definition of impulse is an integral. This assumes the possibility that the force may not be constant over your time interval. I also want you to understand that last year on the AP exam, they had a force that was something like -3t squared plus 5t, and you were asked to figure out what the impulse was over some time interval. So you had to integrate this from 0 to like 5 seconds or something like that. This is not an unrealistic way that we should expect it to be on the AP exam. We will not be doing this during the first semester, but I will be going back to this second semester and making sure you understand that that's what a real possibility looks like. I bring it up, though, too, to remind us that you could use that to find a different way of expressing Newton's second law, and that this is the actual expression of Newton's second law as he expressed it. He didn't say net force equals ma. He said that force was equal to the rate of change of momentum. And this allows for a greater range of application, because momentum isn't just mass and velocity, it's a combination of both, and both can be changing. Rocket problems, rockets use 98% of their mass or 95% of their mass, depending on what kind of rocket we're using and where you're going, and they use that mass usually in the first 11 to 12 minutes. You can't count on m being constant, especially in very dynamic situations. So I bring this up, this is what we talked about on Friday. What I didn't bring up on Friday was something like this. This is a very common question. This is a picture of two objects having a collision. And during that collision, there's a point in time when they are in contact. If you line up the collision has a starting point and it has an ending point. In this collision, the time that they are in contact is this amount of time. Obviously, one object experienced a positive force, while the other object experienced an equal and opposite negative force. That has to be Newton's third law, correct? The thing I do want to point out to you is that if you're paying attention, the area here would have to be the product of force and time, suggesting that the area here is the impulse. The area under a force versus time graph is impulse. Positive impulses increase momentum, negative impulses decrease momentum. This is for one-dimensional motion, of course. So you could say positive impulses are to the right and negative impulses are to the left. Okay? Remember, impulse is a vector. So this was most of what we talked about on Friday, with me throwing this in to let you know that this is the most common way you'll see impulse charts on the multiple choice section of the test. It's common for them to give you a force versus time graph and ask you questions about impulse, change in velocity, stuff like that. All right. I didn't put one of these on your homework. Couldn't find a good one and didn't make one because I limited time. And so if I had to sacrifice something, I'm sacrificing this. It's not likely to be on your semester exam. All right. I want to move on to today's lesson. Are you ready for today's lesson now? Got enough review? Oh, momentum is m times v. And We know that impulse is the same units as momentum, which is kilograms meters per second. Take a minute and draw this picture. We're going to draw some stuff on it. I think it'd be in your best interest to have it. This is supposed to be a picture of, some carts on a track. We're going to have this be the before case. This is during. This is after. Let's start by saying that this cart has a mass of 500 grams, and this is a mass of 1,000 grams. And let's give this cart an initial velocity of 2 meters per second. They have a collision, and after that collision, the carts may have some other velocities. We'll talk about that when we get there. So today we're talking about collisions. There are multiple types of collisions. Right now we are looking at one-dimensional collisions, but obviously collisions occur in multiple dimensions all the time. We will find some results by analyzing the one-dimensional collision that apply to all collisions. So that's what we're going to do today, is we're going to apply some results from things that we know about to make predictions about collisions. But a collision occurs anytime one object becomes in contact with another object. That's a collision. Now, whether that collision transfers momentum or not depends on the conditions of the collision. And that's what we're going to be talking about today, whether there's some momentum transfer here. But ultimately, in a collision, one object comes into contact with another. Those two objects constitute what we call a system. A system is a collection of objects. And in general, we can isolate systems. To isolate means to ensure that they have no external force acting on the system. Also, we can observe what happens to a system. We know some things about systems. For example, we know that a system has a center of mass. We talked about that already. And I'd say that the center of mass of this system is closer to the 1,000-gram cart than the 500-gram cart, because the 1,000-gram cart has more mass. Now, we know how to calculate the location of the center of mass, but it should be clear to you that in this system, the center of mass is moving, right? Do you see why that has to be true? The first cart is moving to the right, closing the distance between the two, which means our center of mass also must be moving to the right. A system has a center of mass, and we would say that the motion of the center of mass of the system will be the momentum of the system. So let me say that very clearly, and I want to use the language I want you to have. A system has a center of mass. The momentum of the system is the momentum of the center of mass of the system. Systems have momentum. The momentum of the system is the momentum of the center of mass of the system. So it's based on the velocity of the center of mass of the system. In fact, we could write this as momentum of the system equals the mass of the system times the velocity of the center of mass. That's how you would write that. You can have hundreds of objects moving in a system, thousands of objects moving in a system. But in any system, the motion of the center of mass defines the momentum of the system. We use these rules to describe the motion of, say, galaxies and solar systems within galaxies, and the way galaxies influence other galaxies. These are all systems. Now, I want to focus on the during part of a collision. Because our system, we could say, has a momentum already. We know the mass of the first car, and we know the mass of the second car. We could compute the momentum of the system by simply adding together the individual momentums. So if you take that to heart, based on what I said a moment ago, if you add the momentum for every object in your system, from object 1 to wherever the last object is, if you added all those momentums together, this would have to equal the mass of the system times the velocity of the center of mass. This would be the momentum of the system. If we added up all the individual momentums. And I forgot to say this in all the other classes today, but it might be worth having a thought about this or a thunk about this, because if you're asked to compute the velocity of the center of mass, this is how you do it. You add up all the momentums of the individual objects and you divide by the mass of the system. That's how you would figure out the velocity of the center of mass. You guys are pretty smart. You could show that the center of mass of the system comes from this. I'm not sure if you're that smart or not, but you might be. So you can prove center of mass from here. But we'll leave that to something to think about. All right, let's get back to where I was talking about. I want to talk about the during part, what happens right here during a collision. Now, the during represents just the time of contact. Now, I want you to think about this for a minute, because although I've said it all day, some people have gotten it, and some people have just assumed that they understood it because they wanted to save face and didn't want the people around them to know they didn't understand. So I'm going to ask this question real carefully. Can you touch the desktop without the desktop touching you? So you understand that car 1 touches car 2 for as long as car 2 touches car 1. Does that make sense? That this contact time has to be the same. Usually in a collision, it's pretty short. Usually they touch for only an instant, but the amount of time that they're in contact has to be the same for both. Now, Newton's third law also tells me that there is a force on car 2 from car 1. And based on Newton's third law, there must be an equal and opposite force on car 1 from car 2. Right? Newton's third law. So that means by Newton's third law, that these two forces are equal and opposite. Does that make sense? Any question about that? All right. Well, I could multiply both sides of this by the time they are in contact, which has to be the same, right? Because car 1 is in contact with car 2 for the same amount of time that car 2 is in contact with car 1. What this means is that the impulse experienced by car 1 has to be equal and opposite to the impulse experienced by car 2. That has to be true. We doing good so far? No big deal? Go back to our example here. In this basic collision comparison, the system had momentum based on the motion of car 1 before the collision. Everybody good there? After the collision, car 1 travels this way at 0.5 meter per second. Okay? How fast is car 2 going? This is a very straightforward conservation of momentum question. Yes, sir?
1.5 meters per second.
Let's work it out. In a conservation of momentum question, we add up the momentums of the objects before the collision, and we set them equal to the momentums after the collision. In fact, what I almost always do is tell you to divide your paper up and say this is the before case and this is the after case, and set them equal. I don't believe we need the picture, but I'm going to leave the picture here of this one. Remember, momentum is mv. I'm not going to put all the subscripts. The stuff that's on the right side is the final case, and the stuff that's on the left side is the initial case. Technically, I should make sure I put my masses in kilograms. If you're just being asked about velocity, you can use any units you want as long as it's the same units for everything. But technically, you should always go to kilograms, meters, and seconds. Object 1 had a mass of 500 grams. It was moving at a velocity of 2 meters per second. Object 2 had a mass of 1,000 grams and a velocity that was 0. This represents the momentum of the system before the collision. After the collision, Object 1 still had a mass of 500 grams, but now had a velocity of 0.5 meters per second. At the same time, Object 2 still has a mass of 1,000 grams, but now has some unknown velocity. I think it's going to move after the collision. Now, before we work this out, I want to remind you, momentum is a vector quantity. And because momentum is a vector quantity, we have to assign positivity and negativity to our directions. I think it's pretty reasonable to make the initial direction of the first car the positive direction. That will suggest that this velocity is going to be negative. Now that means the left side's 1,000. The right side is negative 250 plus 1,000 V2. Do a little math. Pretty straightforward. Any questions about this? All right. Why don't you try one real quick? Because I want to show you something. And I'm not trying to trick you, but you might be tricked. Fair enough? Let's say we do everything the same for the beginning. I'm going to erase all this to get it out of the way. So we do everything the same in the beginning, except after the collision, this cart's moving this way at 0.5 meters per second. Find the velocity of this car. I'll wait patiently. All right. You did 500 times 2, correct? Plus 0 equals 500 times my unknown velocity plus 1,000 times 0.5. Is that what all of you did? Seems reasonable, right? That's 1,000 equals 500 V1 plus 500. So you did your arithmetic and found that V1 equals 1 meter per second. Do you know why that's impossible now? This answer is positive. That means it's going this way at 1 meter per second. But it's behind a car traveling in the same direction. It's going 0.5 meters per second. The only way that would have been possible is if this car passed through this car. Correct? There'd be no way for this to occur otherwise. So although every possibility seems likely, not every possibility actually happens in nature. This would not happen in nature without car 1 passing through car 2. Now, I just made up a number that I knew wouldn't work. Do we understand? And the other thing I also want to point out is it's not like every possibility can occur, but it's also not like you can do anything if you don't know something about the outcome. What if I had not given you either of the velocities after the collision and told you to figure out what happens after the collision? Do you realize you would be unable to do it? Because if all I know about is the initial velocity of one of the objects before the collision, that's going to leave me with 2 unknowns after the collision and no way to solve for either of them because I have no other information. So in momentum problems that have collisions, generally there's got to be a way to figure out something about either the result or the initial conditions that leaves you with a single unknown. You follow what I'm saying? You need to know something about the answer generally. Now, there are situations in which these situations that we've just described right here, these kinds of collisions, all fall into a couple of categories. You can figure out the answers, or at least have less information presented so that you can figure out the answers. The first are a set of problems called inelastic collisions. These are the most basic forms of collisions. In these collisions, the momentum of the system before the collision equals the momentum of the system after the collision. What makes them inelastic is that in all of these collisions, which is the vast majority of all collisions in nature, kinetic energy is not conserved. The initial kinetic energy will always be greater than the final kinetic energy. In most collisions, some energy is going to be transformed into other types. They make noise, they damage the objects, heat's generated. In all collisions, we're usually losing kinetic energy. In fact, in the most extreme, we have what's called perfectly, which is a stupid thing, perfectly inelastic collisions. I say stupid because it's a perfectly inelastic seems like, well, what's perfect about it? It's kind of a dumb statement, but it is a definition. In a perfectly inelastic collision, the objects stick together and have the same final velocity. In these collisions, they generally maximize the amount of kinetic energy lost. That's why the word perfectly is used here. It ends up being a maximum for kinetic energy loss. Now, of course, if I have an entire brand of collisions known as inelastic collisions, you understand that there's probably another type of collision too, huh? Elastic collisions. Elastic collisions, and if they say something collides elastically, they are giving you a piece of information. If they say it's a perfectly inelastic collision, they are also giving you a piece of information. But if they say the collision is elastic, that the two objects collide elastically, the momentum of the system before and after will be equal, and the kinetic energy of the system before and after will also be equal. In an elastic collision, they conserve both momentum and kinetic energy. Now, in all of these collisions, energy is conserved. I keep using the word kinetic energy. Energy is always conserved. It's just usually transformed into a type of energy that we can't use readily, like heat or sound or something like that. So when we're talking about what's being conserved here, we're talking about momentum and kinetic energy specifically. Now, what this should elicit in you is that if it's an elastic collision, you can generate two equations. You can generate a momentum equation and you can generate a kinetic energy equation. We're out of time, but I think you know where I'm going with that. There's an implication here. So let's consider the implication. If the impulse on car 1 is equal and opposite to the impulse on car 2, that means the change in momentum of car 1 has to be equal and opposite to the change in momentum on car 2. Good so far? Well, by definition, change in is final minus initial. So P1 final minus P1 initial has to equal P2 final minus P2 initial, but has to be opposite. All good so far? Distribute that negative sign. P1 final minus P1 initial equals P2 initial minus P2 final. Is that right? You just switch them? We all good? I want to collect the initial states and the final states. So I'm going to move this over here and this over there. And I get P1 final plus P2 final equals P1 initial plus P2 initial. Now, this states something, that the momentum of any system stays constant. Right? The total momentum of any system stays constant. Now, the way I'm supposed to say that is that the momentum of any isolated system. If the entire system is experiencing an unbalanced force, then you can be changing the momentum of the system. But if you have an isolated system, individual objects can change momentum, but the net momentum of the system stays the same. In fact, you could write this as delta P for a system equals 0 for an isolated system. This is a statement of conservation. In this case, conservation of momentum. Conservation of momentum is probably the most powerful momentum rule in physics. In fact, it might be one of the more powerful rules in science. There are no exceptions to conservation of momentum. Clearly, it's a conservation rule. But unlike conservation of energy, where there are so many different forms of energy, there are only two forms of momentum: linear momentum and angular momentum, and they are different measurements completely. They don't mix. So when we're talking about conservation of momentum, we are talking about something easy to see, easy to measure, and there's only one type of momentum that we can measure: mass times velocity. So there are no exceptions to this rule. The issue is knowing when a collision begins and ends, and when we have to stop paying attention to momentum and start paying attention to something else. That's the critical part. So in your notes, make it very clear right now that any collision is the instantaneous moment before contact and the instantaneous moment after contact. That's a collision. It's the instant before they touch and the instant after they touch. That's what we're comparing.